Bilao. So, hi everyone. It is our great pleasure to have here today Professor Nada Lavrats and Dr. Senja Polak from the Johann Stefan Institute in Ljubljana, Slovenia. So Nada is, for most of us, I think needs no introduction, is one of the leading figures of machine learning in Europe, one of the people that set the foundations for inductive logic programming and multi-relational data mining, things like that. So it's a great honor to have her here with us. Dr. Senja Polak is a researcher at the same institute in Ljubljana, and she's doing work on NLP, coordinating several research projects, Horizon and Horizon Europe projects. So it's a great pleasure to have them here today. The title of the talk is Selecting Techniques for Relational and Text Data Analysis. So Nada, the floor is yours.
Thank you very much. Thanks for the invitation. It's a pleasure to be here. We are here on a project meeting, which will start on Wednesday.
Okay, I thought it's not connected. Okay, okay, sorry. What are you doing?
Yes, everything is good.
Okay. So it's a great pleasure to visit you here. Just to recall where we are a small country in Europe, Slovenia, neighboring Austria, Hungary, Italy, and Croatia, and Ljubljana is our hometown. And we work at Jožef Stefan Institute. It's an organization which was established in 1949 after the Second World War. It's named after Jožef Stefan, quite a famous physicist who was born in Slovenia but worked in Vienna. And he's known for this famous formula of the black body sigma t to the power of 4. We come from the Department of Knowledge Technologies. About 45 researchers work there. I was head of department in 2014 to 2020. And we also have our own international postgraduate school, where we teach at the master's and the doctoral level. We have 4 programs: ICT, Nano, Eco, and Sensor Technologies. And it's about 20 new doctoral students who subscribe to this very much research-oriented PhD programs and master's programs. My own research interest is in machine learning, recently also text mining, data mining, and text mining workflows, and also computational creativity with applications in medicine, bioinformatics, and public health. That was the department when I was the head of department, and at that time we still had this department member. Well, we still have him, and he is in charge of promotion of science. So my talk will be about relational learning, and then I will switch to learning representations, and then I will present some of the kind of inductive logic programming techniques which are based on transformation of data from its original form, typical in the form of relational databases, into the format which is tabular, which is appropriate to be used by any machine learning algorithm. After that, Senja will go into selected text mining techniques. So you all know what is machine learning. The simplest form is that we have tabular representation as the input. We have some machine learning algorithm which transforms this input into typically a model which can be used for classification, categorization, prediction, but also some machine learning algorithms are capable of pattern analysis. They are usually called data mining algorithms, and then you can, the result would be association rules, groupings, or whatnot. And the difference between some algorithms is that they are symbolic and they result in explainable models, whereas neural models are improved in terms of classification accuracy. However, they are not directly interpretable. And there is a lot of research going on in trying to interpret the black box models, which are, as I said, more accurate, typically more accurate than symbolic models if enough data is made available. My special interest is in relational learning. The input to a relational learning algorithm is typically a relational database, but we are also, our common interest is in inductive logic programming. So the input to a relational learning algorithm could be also a set of logical facts and a set of logical rules as background knowledge to the learner. Moreover, in relational learning, we can handle complex relational structures, such as the one on the picture, where we could see that it would be not that easy to represent such complex structure with a simple tabular representation. We could represent it, however, in the representation of relational databases. If we had a molecule which has some properties, and the molecules could belong to some classes like mutagenic or non-mutagenic, and then molecules consist of atoms. It's one-to-many relationships between molecules and atoms can be connected between themselves with bonds, which can be single bonds or double bonds. And all this could be represented in the form of a relational database. There is a little missing detail on this slide, which kind of disappeared, but it's okay. Now, the new trend in machine learning are artificial neural networks. Typically, deep learning has several layers of such a neural networks. And the nice thing about deep neural networks is feature construction at the deeper level of the neural network. And this is nicely depicted here. If we would like to distinguish cars from kangaroos, then cars would sooner or later get described at lower level of a neural networks with really nice features which would separate cars from kangaroos. And that's the strong point of neural nets. Neural networks, especially deep neural networks, outperform standard machine learning when enough labeled data is available. Now, if we look at the KDD process, starting from the data, taking into account background knowledge, data transformation, and then machine learning, and finally evaluation and explanation of machine learning results. That is the crisp data mining methodology. Most of the research in the 40 or 50 years of existence of machine learning was focused on the development of new machine learning and data mining algorithms. However, nowadays, there is a shift of focus of machine learning research on one step before, namely, how do we transform heterogeneous data into a simple tabular vector representation of the data, which could, at the end, be used as input to any machine learning algorithm. So this is called representation learning, and there are new representation learning conferences which are becoming more popular than machine learning conferences nowadays. Data representation is, of course, very crucial for machine learning. That is the form, data representation is also called representation learning. And for effective machine learning, this is really a crucial step. So how to transform the data into feature vectors. Our own research was very much involved in this transformation step for transforming heterogeneous data into tabular or vector representations. And we have done that very long ago. We started with that research, and we have now fine-tuned it. So what is the advances? That we get explainable transformed data, we get explainable models, as an output, but these models would typically be slightly less accurate. On the other hand, neural data transformations, which are extremely popular nowadays, also called embeddings, they are transformations into numeric feature vectors. And they are dense, compact representations into maybe a fixed set of dimensions, such as 200 dimensions, or that is a parameter of the representation learning algorithm. And these are numeric feature vectors. With that, we typically achieve better accuracies, but lower explanation power. So our own work was very much focused on the symbolic data transformations, where the input would be a relational database. And after some clever feature construction, we would get new features, which did not appear in the original descriptors. And then these features would be evaluated for each row of the main table. And the features would be evaluated as true or false for the given row of the main table. So here we have three interconnected data tables, one about customers, the other about orders, and the third one about stores. If we are interested in the orders, we would have such a transformation of the data after propositionalization. And the features would be explainable, and then we could typically use any machine learning algorithm on top of that to get other classification models like decision trees, of course, or whatever type of, let's say, patterns like association rules or classification rules. It's interesting to note that also in text mining, the original representation of texts was sparse data representation in terms of sparse vectors. So the most intuitive representation of documents would be through words which appear in the document. Of course, there are some pre-processing steps needed, like stemming or lemmatization, chunking away irrelevant words, and so on and so forth. But once we have a vocabulary of words which appear in the entire data collection, in the entire set of documents, in the corpus, we would put all the words as features, and then the feature, if the word appears in the document, it gets number 1. If it doesn't appear, it gets number 0, and it is a sparse representation of documents, because in a data collection, you could have, let's say, 1 million words, and then obviously there would be very few ones and very many zeros. However, just to see that it's the same trick of kind of transforming data into a vector representation, like in propositionalization, once we get this set of vectors, we can use, in principle, any machine learning algorithm on top of that. Of course, some algorithms wouldn't work very well on such sparse data representations. Nevertheless, in text mining, usually the representation is not in the form of zeros and ones. Some representations would be based on term frequency. So we would count how many times a word appears in a document and would simply put a count. However, the standard representation is so-called TF-IDF, which is a measure between 0 and 1. It is high, close to 1, if the number of words is very frequent within the document, but this is counterweighted with the frequency within the entire document collection. If we have one word which is very frequent in all the documents, then it shouldn't have a high weight. Nowadays, embedding of text documents, as I said, you would have a fixed number of dimensions, maybe 200. You would have numeric values for these feature vectors representing individual documents, and you could still do classification either with any machine learning algorithm capable of dealing with numeric numbers or with a neural network. And the feature weights would typically correspond to the weights in the embedding layer of a neural net. In addition to document embeddings, of course, you can have all sorts of other embeddings like corpus embeddings, but also word embeddings. The nice thing about word embeddings is that when you transform words into the features in the n-dimensional vector space, we would have a particular word, banana, which would be represented by such numeric values in 200 dimensions. Then we could plot that into two-dimensional vector space. Then if we would plot another word like mango in this same two-dimensional vector space, we would have another vector, and so on and so on. And it would turn out that the words which have a similar meaning would have a similar representation in the n-dimensional vector space, and the similarity could be also computed and used for modeling the language. Senja will talk a bit more about that. So in our book, which we recently published, it's a book by myself and Marko Robnik-Šikonja from the Faculty of Computer Science and Informatics of the University of Ljubljana. We wrote a book in which we tried to unify the two frameworks on propositionalization and embeddings. And our colleague Vilt Podpechan implemented a number of propositionalization and embedding algorithms in the form of Jupyter Python notebooks, which are now made freely available to the research community. One of the side effects of this work was also a joint framework for propositionalization and embeddings, where we compared the two frameworks and discussed the strengths and weaknesses of one and the other. So in the rest of my part of the talk, I will just illustrate three different technologies which use this trick of transforming data into feature vectors. And these propositionalization techniques will be very briefly outlined. Before going into the propositionalization of transformation of relational databases into feature vectors, I would also like to mention another part of my own research, which is so-called semantic data mining, where in addition to the data, we take into account background knowledge in the form of ontologies or taxonomies as part of the learning input. That's what we call semantic data mining. And recently, we are also very much interested in learning from knowledge graphs. And knowledge graphs are becoming the omnipresent technology for representing knowledge in very many different domains. And that's also the scope of our recent research. In terms of propositionalization of relational databases or relational data in general, we have quite a lot of work. It started in 1991 with the development of the Linus algorithm, and then RSD algorithm for relational subgroup discovery. This was in collaboration with Filip Železný from Czech Technical University. Competitive algorithms were 1BC by Peter Flach, RELF by Czech Technical University, and Aleph, especially ILP. Aleph is the best kind of ILP learning algorithm, but it has also a featureized facility with which you can transform the data into feature vectors. So we were comparing our work with the Aleph featureized algorithm. Then we developed wordification in 2015, and recently within the work on kind of integrating propositionalization and embeddings, a PhD student of mine developed two new pipelines which combine propositionalization and embedding steps. So just to go into RSD very, very briefly to show you that at that time we were still using the logical representation. So we have logical facts as data. Here we are talking about the genes and their gene expression. And we are trying to find genes which are similar for different types, for the positive versus negative examples. From the gene ontology, which consists of information about components, functions, and processes of genes, as well as interactions of genes, which are binary relationships. So the first three just talk about the properties of genes in some gene ontology terms, and then we can automatically try to generate some relational features, which will be then used in the transformed data representation. So for instance, feature 2, we say, aha, atom A belongs to the concept gene ontology 0016020, and so on. On the other hand, gene A, let's say, belongs to this function, has this process, but also maybe an atom, gene interacts with another gene, which has another function and it has another component. So we would automatically construct such complex features like that. We could construct features consisting of a single term, of a conjunct of 2 terms, conjunct of 3 terms, and this would be our feature generation process. Once we have generated those features, we would put them as attributes in the data table, and we would evaluate the features as being true or false for the given data. So here we had differentially expressed genes. This would be class A, or random genes. This would be class B, and we would try to differentiate differentially expressed genes compared to random genes or non-differentially expressed genes. Once we have such a feature vector representation, we could do pattern analysis, like if feature 2 and feature 3 is true, then class differentially expressed. But of course, we could build classifiers out of such representations, and this would be symbolic classifiers. Another approach, wordification. This was quite a neat approach which we have developed. It uses a very simple trick. Suppose we have a main table which is connected to other tables. Let's say this main table is connected to this, and this table is connected to this one with one-to-many relationships, and this table is connected to this one with one-to-many relationships. So we should note that propositionalization and all these transformation approaches are really appropriate for modeling one-to-many relationships in relational databases, and much less to many relationships. Anyway, once we have that, what was our trick? Our idea was to transform this main table into feature vectors, another table into feature vectors, each of these into feature vectors, and then simply concatenate the feature vectors which were constructed going along the path of a single data sample from the main table and concatenating that. And what are the features here? Very, very simple features. Table name, attribute name, value. Just feature values would be the features which we would construct. And then when we have such features, which we would just concatenate them into bigger feature values. And in order to model the interdependencies, we would construct n-grams. So let's say, if we had this table about customers and orders, if the main table were orders, we would say order, order number, value, and so on and so on. And then we would go into customers, customer 1 living in here and there. So unfortunately, I didn't put an illustrative example here. But these features are really very simple, constructed by attribute value. And now the trick is, once we concatenate them, we get a kind of textual representation. we get sparse textual vectors. And then on top, we can use all the text mining technology. We can use TF-IDF on top. We can use whatever other algorithms like in any text mining approach. Funnily enough, it turned out that with this extremely simple approach, we would get the same accuracy as Aleph featureize, but we could get a significant speed up of up to 100%. And this took some pace also by approaches of other colleagues in Europe and in the world. I mentioned two other pipelines for relational data analysis, prop DRM and DeepProp, recently developed, combining steps of propositionalization and embedding. I will present very briefly two other approaches based on data transformation, where we go to other types of more complex relational structures. Other people's work is entity embeddings like star space, graph embeddings like Node2Vec, DeepWalk, our own work SNOR algorithm in 2020, then embedding of heterogeneous graphs like MetaPath2Vec, knowledge graphs embedding like RDF2Vec, embedding of text-enriched heterogeneous information networks. I will present this approach. So it goes into even a more complex data structure compared to knowledge graph embeddings, because some nodes in the knowledge graph would incorporate texts themselves. Then some work of improving semantic data mining by speeding it up through NetSDM, and some neurosymbolic representations of ontologies of text. We had Tax2Vec and Autobot developed recently. So let's go to this TechMine approach to embedding text-enriched heterogeneous information networks. So what is a heterogeneous information network? It is a network which is a heterogeneous graph. In such a graph, we have nodes which are of different types, like scientific papers are published in proceedings of conferences. Conference ECML 2010 and 2009 are part of a group of conferences ECML. We have papers, we have authors of papers, and two papers can be co-authors of the same paper, and one paper can be connected to other paper through the sites relationship. So this would be a heterogeneous information network, or typically a knowledge graph. And a text-enriched heterogeneous information network would be the one where in some nodes we have actually texts. So in one PhD thesis of Micha Gercher, we did the following. So if we have such a heterogeneous graph, for each node of the graph, the one, let's say the selected node being marked red, and we have different types of relationships between different types of nodes, a relationship co-author between two people, a relationship of sites between two papers, and a relationship of same event between two conference occurrences. So now for a particular node, it is enriched with text, and it appears in different contexts depending on the type of relationship which we take into account. Now, each of these are considered a different structural context, and the text itself is the text. So what is the trick which we used here? We used network analysis techniques, especially the personalized PageRank, to estimate the importance of features, namely the importance of terms. Oops, this is a wrong slide for the previous There is a missing slide here. So it is not there. Anyway, I will mimic what should happen here. So this part would be transformed into a bag of words feature vector representation. This guy would be mimicked as a set of numbers, which would be obtained by personalized PageRank. When personalized PageRank would run around always from this node. So that would be the starting node of personalized PageRank. And then the random walker would once go here, another time would go here, another time it would go here, and so on. And obviously this node would get a higher feature weight because whenever you would go, in most cases, it would go here. So this would be the highest, and then that would be the second highest number for the personalized PageRank going from this particular node. And this guy would be running through the context of this relationship. And here, the personalized PageRank, also starting from this node, would only visit nodes which are connected through this relationship. And finally, this guy would be running around through the network consisting of nodes of this relationship only. For it,
sure that I understand. So each of those graphs is not homogeneous.
is homogeneous, yes.
It's always possible.
Yes, each context is represented with a homogeneous graph. And for each of them, we get a feature vector. All these feature vectors would be of the size of the set of nodes in which one particular relationship, it is a subset of the original set of nodes. So we would get a feature vector like that. However, for the types of nodes which are of different type, we would get a 0 because the random walker would never visit those guys. And then we would take these feature vectors and we would, again, and here we would have bag of words representation. And then the trick would be that we get the bag of words representation and concatenate it with the feature vector from the first context, from the feature vector of the second context, and the feature vector from the third context. So now for each node, we would get such a vector representation. So sorry for missing these slides, which should be there. And finally, the net SDM approach, again, using this idea of personalized PageRank, combining network analysis approach with graph analysis approach, aiming to reduce the complexity of searching of the space for semantic data mining. So here again, what do we have? We have the data. We have some positive examples, some negative examples. Each of the examples is related to some node in the ontology, like gene ontology. Now we consider the gene ontology as a graph. We see which nodes are important within the graph for the data which we have available. Here we again use the personalized PageRank approach, running around the ontology nodes. In the second step, we described the nodes which are less important in the ontology. And now we use this reduced ontology for semantic data mining using our data. And we get some explanations for the positive and the negative examples in the data. So if I look at this in the application for ALL, this is acute lymphoblastic leukemia. Suppose we have the positive examples of ALL compared to the negative examples. In the data, we connect the examples to the concepts in the gene ontology. After reduction of the gene ontology, which we get an ontology with a reduced number of terms, and then we can use these terms in explaining the data. For instance, we can get the characteristic property of ALL, that the genes which are characterized by immune system process and self-surface receptor signaling pathway and plasma membrane and binding would be characteristic for the positive examples of ALL. So with this, I would wrap up my part of the presentation. Propositionalization and embeddings have some positive properties. First of all, these are quick and automated transformation methods. Any propositional learner could be used on top of such transformed representation. Semantic similarity of instances is preserved in this transformed feature vector space. And now in embeddings, due to compact representations, this semantic property of similarity preservation is even more exposed in the embeddings. Strength of propositionalization is, of course, in the understandability of the features which have been constructed. However, the strength of embeddings is in improved compactness, improved and faster learning based on that. Also, a very large number of data types nowadays is covered with embeddings, including text, relations, graphs, images, time series, and so forth. And there is a very wide community of developers nowadays in this area of research. Limitations of both is that when we use them in multi-relational learning setting, in propositionalization is limited to one-to-many relationships, cannot handle recursion, cannot be used for predicate invention, obviously. And also, if we would really like to get understandable features, we would be kind of limited to Boolean vector sparse Boolean vector representations. And of course, sparse vectors are not a very good input to any really very memory efficient machine learning algorithm. Limitations of embeddings would be, of course, in the loss of explainability of features and trained models. So it would be kind of black box systems. And of course, there's a lot of research now going on to the explanation of deep neural networks and in the explanation of embeddings. So it's again a separate research area. And of course, also high memory consumption due to so many weights in a neural network, so requiring specialized hardware. So we would switch then to Senya's presentation, but I could take some questions now on my part, maybe while you are still, just after processing my part of the talk.
Thank you very, very much for this part of the presentation. I have a question regarding you claimed that that the semantic similarity is retained across the transformation. I think it was 2 slides prior. How are we certain of this? It's exactly because the features retain their semantic, let's say, their meaningfulness.
Yes.
Okay, so essentially we can, once we have this mapping, then we can revert and convert again these features to words, right? So it's a two-way transformation if we need. That's the claim, I suppose.
Yeah, but let's say in this n dimensions, like 20 dimensions representing the word banana or mango, it would be very hard to know what does dimension 1 mean.
Exactly.
Or dimension 200. What is the meaning of these dimensions? Once we plot them in the vector space, we can see the similarity of the words banana and mango being very close to each other in the 200-dimensional vector space. But what is dimension number 23? Exactly. That's very hard to understand.
Okay, so the cause for this is exactly that per dimension you retain the meaningfulness, the explainability of the specific dimension.
Yeah, I agree. It's you get the semantic explainability, but not through the individual features.
But on the whole. Okay. Thank you very much.
Any other questions on this one?
Okay, thank you. Oh, can you hear me? Okay. Okay, so I will continue with text mining and natural language processing, more from presenting some of the applications that we developed recently. I will focus especially on the Embedia project, which we just finished recently, but of course the work continues through other national projects. So Nada already in fact introduced what are word embeddings. There was even discussion on that. Maybe just some background. So the underlying idea behind this is distributional semantics paradigm. So basically is that you know the words based on the context where the words appear. So since we are in Greece, I selected the example of ouzo, right? So if in many countries you don't drink ouzo, but even if you come to a person that never tasted ouzo and you give him these sentences, a bottle of ouzo is on the table, everybody likes ouzo, ouzo makes you drunk, and we make ouzo from grape must. You don't have to taste ouzo to guess what is it all about, right? You would be able to deduct from the context that it's a drink, that it makes you drunk, probably it's alcoholic drink, and so on. So basically the context of words tells you a lot about the meaning of the words. So that's the hypothesis behind. And what Nada already explained, so basically either you, from simple co-occurrence of words in a corpus, the words that have similar meaning would appear in similar contexts. Therefore, let's say cherries and strawberries would appear in recipes and in the pies, and they would have more similar vectors than, let's say, information and digital, which would be then also more closer in this semantic space. And nowadays, so instead of these co-occurrences, you try to learn the representations automatically with deep neural networks. And basically, either you try to predict, let's say, the word from the context or the context from the words. And then you have these dense representations that Nada introduced. And because of the context, if we come back here, so at least in European countries, you would say, I eat a banana, I eat a mango, and they are close in the embedding space, but you don't eat a dog, and therefore this is closer apart. And you don't eat a computer, which would be also more distant. So the nice part is also that in this vector space, you can make different kind of operations. So one of the properties of embeddings is that they preserve semantic relations, and you can also compute the analogies. So the relation between man and the woman is very similar to the relation between uncle and aunt and between king and queen. So this is sort of gender dimension. And it can go even broader. So if you have adjectives slow, slower, and slowest, and then you would like to, you have the adjective short, by analogous computation, you would know that shorter and shortest are, have similar relations than slow to slower and slowest. So in terms of word embeddings, there are different embeddings types. So it started with static embeddings, where you try to represent a single word, a single token, and you assume that word has one meaning, which is defined by the context. So nowadays, we talk more about contextual embeddings, So contextual embeddings basically in each occurrence, in each sentence, the token or the word would have its own representations. And then let's say that you have polysemous words, which have two different meanings. They would group these meanings into two clusters. And basically, since we have each occurrence presents its own representation, you can then also compare how the word is used across different corpora or across different time periods. I will show some examples later. So for our projects, maybe the most important was the development in multilingual embeddings. So since the embeddings are learned on multilingual corpora, you can also have applications which go across several languages. So basically, if we just talk about representation, you can say that nice weather, it's very close in embedding space to the bouton, but this can go beyond the simple tokens. It can go to entire sentences and documents. So another, let's say, development in the field, which really influenced a lot of results, is that the technology is now based on transfer learning. So we don't start from simple documents of our corpora where we work, but we start with large pre-trained language models that are made available, so learned on huge amounts of data from Wikipedia or much larger Google collections of text. And this already contains the general knowledge, multilingual or monolingual models. And then we only apply it to specific tasks, so we fine-tune these models, and therefore we preserve general knowledge about relations between words, and only from there on we apply it to specific tasks, which makes the learning much easier. So in Embedia, the main question was, how can we transfer the tools from well-resourced languages to less resourced languages? So since we are in Greece, I believe the situation here is quite similar. So we know that in many communities like natural language processing, you have, for many years, there were data sets in English and everyone was competing in English language, and you have million data sets, million tasks, million tools, and the entire competition is going on there. And then you come to less resourced European languages. Basically, there are resources available, but there are no data sets, no annotated data sets, much less annotated data sets, much less available trained tools, and so on. So basically, the idea is, how can you quickly adapt the tools available from other languages to your language? And here, so the majority of work was based on this MBERT and now XLMR and other multilingual language models. So basically, if you have a tool for sentiment analysis, if you have English data available, you can then train the tool with multilingual model and directly apply it to Slovene. So if you have no Slovene data, it would be called zero-shot learning, so learning without any examples in Slovene. If you have some available examples, it would be called few-shot learning setting. Or of course, if you have data available, you would be building also monolingual models or just multilingual models. So the project was interested in less represented European languages, especially Estonian, Croatian, and Finnish, Latvian, Slovenian. And we were interested in AI applications for media industry. We had 3 companies involved who were interested in actual tools. And the idea here was also that there is also in the news industry, you have big companies like Bloomberg. They have entire AI departments with a lot of money that they invest, while the companies in smaller countries, they don't have such huge technological departments, so that they would build each tool for themselves. So we were trying to make like these fast solutions for some of the main problems that they have. So the project ended in 2022, and we were interested in comment analysis, in news analysis, as well as in news generation. So in the project, we built several pre-trained language models. So before I mentioned these huge multilingual language models like multilingual BERT or XLMR, but it turns out that if you want to have good applications, it's still better to train your own monolingual models, which are of higher quality because you have more data, or even specific like English, Croatian, and Slovenian model would perform better than the general multilingual one. And then we developed also a range of evaluation tasks. Before I was talking about analogies. So for instance, I presented the gender analogy, but a similar one would be like, what Athens is to Greece is Ljubljana to what? The correct answer is Slovenia. And if you want to develop cross-lingual testing, you would put a pair in a different language, so to see if you have a good multilingual representation. So then in terms of news media applications, we developed a range of methods for named entity recognition and linking. So basically, if you have news, you want to recognize the persons in the news, the locations, the organizations, and even link them to the entities in Wikipedia. So here we were experimenting a lot with monolingual and multilingual methods, trying to see like if resources annotated in similar languages can improve the performance for the same group of languages. So then one of the main applications of our interest were keywords. So when you have media companies, here we worked a lot with an Estonian media company, recognizes the main keywords in text are very important. So they currently do it manually. I mean, before they did it manually. And for each article, the journalist defines, or the editor defines 5 keywords. And this is in fact behind linking of the news, organizing the news in an archive and so on. And here they really need our, they really appreciated our solutions. So we tested several different, we developed several different solutions from a totally unsupervised ones to supervised ones. So at the end, the supervised one worked much better. So basically we took their archive where they have already these manually annotated keywords. And then we developed a sequence labeling system where from the text learns how to predict which sequence of tokens it's a keyword. And yeah, they were quite happy with the results. So they actually implemented it in their workflow. And then from scientific perspective, we also tested if this can be used in cross-lingual setting. So if you have training data in several languages, you know which are the keywords, can you use it on another language without any training data? So the sequence labeling. Okay, I think it's okay, yeah. So the sequence labeling approach, basically for a sequence of words, you would try to learn which sequences are to be kept as keywords. At the end, you would have the sequences, let's say, these are keywords and all the rest are not keywords. And in our approach that we developed, you need a very small data set, which was an added value, and it was developed for many languages. But as I said previously, so if you don't have any training data, either you used unsupervised methods, which are usually not very good. So basically there are several methods which have much lower performance, but you don't need any training. And then you have training data, which leads to much higher performance. So what we tried here is that we tried to learn a system only with the data from other languages. So we called it leave one out, we leave one language out of the training. And we showed that even if it's much worse than if you had the training data, these approaches are better than unsupervised learning approaches. So then another part of work focused on sentiment analysis. Here we were interested whether news contain positive, negative, or neutral sentiment for the reader. Here we had a data set in Slovene, but in fact, our Croatian partners were interested in using the tool. So here we went to this zero-shot learning setting that I mentioned before. So there were no data available in Croatia. We just learned the multilingual model, and we just annotated a small amount of Croatian data for evaluation, just to know how well it works. So it was a bird-based model. We had two training objectives. So basically one was about the entire article sentiment, one was on paragraph level. And we also experimented a bit with long document representation because BERT by default takes only 512 tokens. So we made a bit better representation. But what is the most interesting is here. So for Slovenian, where we have training data, we have results around 66 F1 score. And we showed that for many other languages, we can have a bit lower, but not that much lower results without any training data, which is quite satisfying. Yeah, so since we have contextual embeddings, so each word in each appearance gets its own representations, we also worked with diachronic and viewpoint analysis. So basically, we looked at corpus and news analysis across time. So if this is an example on COVID news data set. So you have each month would be part of the corpus. And let's say that you have the word diamond. And you have the representation of word diamond, and you cluster the representation, the embedding that appears. You cluster them by similarity, and you group them. And then you compare the distribution of different clusters across time. So you can see here that you have a very different distribution from January to February. And in fact, it was when Diamond Princess, the boat, if you remember, when COVID outbreak was there, it was about Diamond Princess. So this is totally different usage than Diamond Industry. So in February, nearly exclusively, the usage of word diamond was nearly exclusively used in the context of Diamond Princess, while in January, it was all about Diamond Industry, Black Diamond, and so on. So we adapted this we used this method then many times. Now, currently, we are working on a literature project where humanists are interested in comparing two different authors, how they use certain words. And we also worked with social scientists who were interested in comparing two corpora, more progressive and more conservative media on LGBT topic. And they, for instance, showed, this was, for instance, an example, like when we talk about the word relationship, again, we have two groups of media, one more progressive, more conservative, with totally different distribution of clusters. And it showed that the more conservative right wing uses the word relationship also in polygamous relationship and in this context, while the left one talks about marriage and children. So this is like with applications to social science. So then the second big part of research was on comment analysis. So basically, if you have news, below news, you have a lot of comments. I don't know if it's here as well in Greece. So usually this is very toxic, it's horrible. And when we interviewed people from media industry, they said that the moderators are totally depressed. That is the worst job that you can imagine, and that they are very, they don't want to do it for a long time. So here we developed many methods, as well as for specific companies with their specific rules, as well as cross-lingual methods. So maybe I will just show this. So here we have an example. So here we have again, for instance, English dataset, which is always available for many applications. And then we have Croatian dataset. So if we don't have any Croatian data, with only English data, you can get quite good results, around, let's say, 67%. And immediately, if you have 10% of data and you use also English results, we got like to 70 to 73%. And if you have 100% of data, basically, this is only 2% less than with the entire data set. So basically we show that with cross-lingual transfer, you can use very small amount of annotated data and adapt your tools with English or other data sets available. We also work with fake news spreader detection, with background knowledge integration, with multilingual Twitter sentiment analysis, and also some work on text generation, including title generation. So in the project, we made a lot of tools available, so everything is publicly available, and it's in fact used also by industry for some of the tools, not all of them. So that was about the project. Then we have, of course, many other applications, including terminology extraction. And maybe one interesting example for the end, it was having this analogy hypothesis. We leverage this hypothesis for generating new knowledge. We work with the Institute of Biology in Slovenia. They defined two different domains, circadian rhythm and plant defense domains. And then basically we modeled the genes in the embedding space, and we said, oh, what is the gene? They know about the genes A and their relation to circadian rhythm, and they were interested in the plant defense domain and wanted to find genes with the similar characteristics. And in fact, they were quite happy with the proposed genes. So now we just applied for a new project, and we will see. So that's all from my side. And yeah, thank you.
Thank you very much. Other questions? Rosanna or Nada?
So thank you again. Okay, there are many common spaces for interaction with the lab. This is very, very clear. One thing I would like to ask is, especially regarding the connection with the humanities.
Yes.
So do you believe that essentially doing transfer learning from one language to the other implicitly adds a cultural bias
Yes,
to the findings?
Of course. I mean, my background from long time ago is in humanities. So okay, there is a lot of cultural differences, but not only cultural differences, even behind each, even if you take just models, right? Each model is trained on some data set. So if you already compare models in English, you would have differences because Wikipedia is totally different from Common Crawl. And you have, even the sociological biases. We were doing some analysis about language model bias, and you have quite funny, if you use masked prompting, you get quite funny predictions for some models for a lot of things. So I believe that, of course, cultural difference plays a big role, but still these systems are so robust that if you take the tasks are subjective. So on one hand, if you take hate speech, inter-annotator agreement between people would be quite low. If you take two different media companies, in fact, it's not black and white. So one will filter out comments very strictly. The other one has a totally different policy. So I believe that all these elements are biases. Language is another bias, cultural difference is another bias, but basically you still get quite good baseline for the tools. On the other hand, it really allows for nice comparisons, right? So if you compare, language models across different languages, with sociologists, we work, for instance, on the analysis of these biases from cultural perspective. But yeah, of course, there are differences.
Excellent. And the second one, so in the biology aspect application, let's say, so the fact that you consider the analogy in the embedding space will mirror an analogy in the real world, let's say, hopefully. I was thinking, so you don't train two different models, you keep the original one.
Here, in fact,
embedding models, sorry, embedding.
No, here we do. In fact, we take PubMed. And in this particular study, this was done in a way that you had two fast text models trained on two different domains. And then we used the alignment of, like, when you have language, two languages, you would have this aligning algorithm of the embedding spaces. And here we did it for
Excellent. Okay,
monolingual. So that was the way that, but I think our next step, if we get it, would be also to use it in so basically you could also use it like with BERT kind of embeddings, and then you would have contextual representations
Exactly.
which would differ across.
So this was the next part of the
Yeah.
question. So I'm fine.
Okay.
Thank you very much.
Thank you.
Thank you. Thank you for the very interesting talk. I don't know whether this is a question for Senya or Nada, but in the current very fast changing world of natural language processing, do you see that ILP can play a role?
Maybe it's
I don't see ILP that much in NLP, in natural language processing. I mean, I know many years ago, ILP was also applied to the problems of natural language processing, but now I don't really see it. Do you?
I mean, no.
Uh-huh.
I think, I don't know if it's ILP or not, but I think like this background knowledge integration, it's really important.
Yeah,
so
yeah,
I
of
don't
course,
know.
knowledge graphs.
Yes.
Um,
I mean, I think like this
Yeah.
knowledge grounding of the models, even if now we see really huge advances, I mean, each day now with ChatGPT and everything. But I think one of the problems with the models, it's still like there is a lot of hallucination, right? And it's very hard to distinguish between facts and hallucinations because everything looks convincing. So I believe this grounding with background knowledge graphs in an intelligent way, it's really important, and sort of some verification of the outputs with symbolic methods. I mean, so I mean, from what exactly it's ILP here or not, I think it's for Nada to answer, but I believe that there is synergy at
I mean,
least in this part.
ILP is in a way defined also with the representation of the data, and this logical representation,
Yes,
I don't see it in contemporary machine learning algorithms like facts or relationships, logical if-then rules in a kind of prologue notation. So it depends what is the definition of ILP nowadays. It's definitely not logic programming, which would be done in natural language processing, I think, anymore.
Yeah, but probably like if you use logic testing, I mean, if the models can compile to some, if they can solve well, or if you can use in pre-training some logical relations, probably you can adapt the language models to be more reliable. No?
It's an interesting question. Now, if our words would be logical expressions, and if our words would be logical facts, and if our sentences would be logical rules, it would be interesting actually to try to do such an experiment, actually, also with language models. And that would be pretty cool, actually. What would be your answer?
Not really. I don't have an answer. I don't have an answer. It's I think it's difficult to have an answer because everything is changing so fast. I just feel that even in computational linguistics or linguistics without computational aspects, you cannot really do away with logic or grammar completely, can you? I mean, I don't think that neural approaches will change linguistics in principle.
I mean, they will not change the linguistics. I mean, you're trying to mimic, right, the linguistic knowledge. I believe you. But it's, yeah, I think it really depends on the tasks, right? I think you have a lot of tasks which are very
solvable. I mean, like with semantics, you can get great results and so on. And then there are some tasks we were just now working with a very specific problem around Buddhist Sanskrit, very small corpus with lexicographical applications to finding, let's say, meanings of the words. And since we are NLP group and of course working in deep learning, like we were now for, I don't know, several months working in developing bird-based word sense induction and so on. And then the lexicographer was really not satisfied with our results. At the end, she said like, oh, this month I just programmed myself something very simple, like I use, let's say, TF-IDF or a variant. It works much better than everything you did. So I think I mean, sometimes we don't think enough about the problem itself. So if you're just looking for some very, let's say, either logical relations or overlap between words, maybe it would be more intelligent to start from there and then develop it further. So
I really actually like your question. So for me, it would be a great challenge to start with an ILP representation, look at logical facts, which are the data as words, and logical rules representing the background knowledge as sentences, and then taking some NLP or deep learning or even text mining mechanism. It would be very analogical to what we did in this approach called wordification, where there was a simple trick how to transform a relational database into a set of documents. So maybe it could be very nice to try that.
Yeah, and I also think that, I mean, now when you have the models, it really all depends on the training objectives that you take, right? You can do intermediate training or even before in the pre-training phase. So let's say if you, here everything is masked on, it's based on this masked language modeling where you hide the words. But there are some approaches like that you try to I mean, I think like a lot of these things could be used in like another objective, additional objective when you are building the language model and then.
And I'm not enough aware of the people who combine learning with reasoning. So maybe that community has some answers to your question. Because I'm not that much into the reasoning component. I'm more in the learning component. But I know Luc Derat, he combines kind of learning and reasoning components, and I don't really know how he does it nowadays. Should I just take the key?
Yes, I can do it. Just a minute so I can eject it.